The wind cut different across the Nebraska plains in winter of 1878. Jonas Erickson learned that his first February when the thermometer hit 5 degrees below zero and his cabin stayed 30 degrees even with the cast iron stove burning all night. He had built his heating exactly the way every homesteader on the Central Plains was told to build it. Good iron stove, steady wood fire, burn prairie chips when timber ran short, standard and proven. By morning, he had burned through more fuel than most families used in 3 days, yet ice still formed on his water bucket 3 feet from the firebox. Across the Great Plains, settlers were losing the same battle in cabins heated by the book and failing by the season. Over the next 2 winters, Jonas quietly buried his stove under what neighbors mocked as a useless dirt pile. What did he understand about heat and fuel that turned his ridiculous-looking heap into a 12-hour burning furnace? The pattern repeated itself across every homestead from the Platte River to the Sandhills. Martha Lindgren, 3 miles east of Jonas, woke her husband twice each night to stoke their stove, or watch the children shiver under wool blankets that felt thin as paper. The Andersons, newcomers from Illinois, burned through their winter wood supply by January, and spent February splitting green cottonwood that hissed and smoked but barely warmed their single room. Even experienced settlers like Hans Mueller, who had survived 5 prairie winters, found himself hauling dried buffalo chips in a wheelbarrow every other day, just to keep frost from forming on the inside walls of his cabin. The arithmetic was brutal and simple. A typical cast iron stove, the kind sold at frontier supply stores for $12, consumed roughly half a cord of wood per week during deep cold spells. Prairie families who could afford timber paid $2 per cord delivered if they could find it. Most relied on gathering buffalo chips, sunflower stalks, and twisted hay bundles that burned fast and clean, but provided heat for barely an hour per armload. A man spent 3 hours gathering fuel to get 1 hour of decent warmth. The labor alone exhausted homesteaders who already worked from dawn to dusk just to survive. Jonas understood the problem because he had lived it, but he also carried knowledge most of his neighbors lacked. His father had emigrated from a province in northern Sweden where winters lasted 6 months and timber was precious. In the old country, families built massive tile stoves called kakelon that stood floor to ceiling in the main room, constructed from hundreds of ceramic tiles and dense clay. These stoves burned wood for only a few hours each day, yet radiated steady warmth for 24 hours. The principle was thermal mass. Instead of sending heat straight up a chimney, the stove captured heat inside heavy materials that absorbed it slowly and released it gradually. When Jonas mentioned this to his neighbor Carl Bergman during a February thaw, Carl laughed outright. "You want to build a big dirt pile around your stove? That sounds like something Indians might try. We got good iron stoves here, Jonas. This ain't the old country." Carl spoke for most of the settlement. Iron stoves were modern, efficient, and familiar. The idea of burying perfectly good cast iron under mud and straw seemed not just wasteful, but primitive. Why make extra work when the current system, however imperfect, was what everyone understood? But Jonas had observed something Carl missed. The Swenson family, recent arrivals from Minnesota, had built their cabin with thick sod walls instead of the standard thin board construction most settlers used. Their cabin stayed noticeably warmer on the same amount of fuel because the heavy earth walls absorbed heat during the day and released it slowly through the night. The principle was identical to what his father had described about the old tile stoves. Mass held heat. Thin iron released it immediately. The social pressure against experimentation was constant and pointed. At the general store in town, when Jonas asked about clay and fire brick, the storekeeper Samuel Morrison shook his head. "Iron stoves work fine if you tend them proper. You're making this harder than it needs to be." The message was clear. Frontier life was difficult enough without abandoning proven methods for untested theories. Jonas was viewed as someone who complicated simple solutions, who brought unnecessary European ideas to American problems. Yet the evidence kept mounting. During a week-long blizzard in March, Jonas recorded temperatures inside his cabin each morning. With his iron stove burning continuously, the interior averaged 42 degrees Fahrenheit. He used 4 full loads of mixed wood and prairie chips daily. His neighbors reported similar numbers, some worse. The Anderson cabin, poorly chinked, never rose above freezing despite constant fire. 3 families in the settlement burned through their entire winter fuel supply during that single week and had to borrow or buy emergency wood at premium prices. Jonas began sketching plans based on his father's descriptions. The concept was straightforward but labor-intensive. Build a proper firebox using fire brick to withstand high temperatures. Surround the entire stove and chimney with a massive construction of clay, sand, and chopped straw. Design the chimney to run through the mass in a serpentine path so hot exhaust gases transferred their heat to the clay before escaping outside. The clay would absorb heat during the burn and radiate it steadily for hours afterward. Instead of heating air that immediately escaped through cracks and thin walls, the system would heat dense material that held warmth and released it gradually. The technical challenge was adaptation. Swedish tile stoves used manufactured ceramic tiles and professionally mixed mortar. Jonas had prairie clay, river sand, and wheat straw. Swedish stoves were built inside stone houses with thick walls. Jonas lived in a frame cabin with board and batten siding. Swedish craftsmen had generations of experience building these systems. Jonas had childhood memories and basic carpentry skills. But he also had precise observations of failure. Standard frontier heating wasted fuel because it heated air instead of mass. It required constant attention because thin iron cooled rapidly. It provided uneven warmth because the heat source was small and centralized. Most critically, it demanded enormous amounts of fuel because most of the heat escaped immediately up the chimney instead of being captured and stored. The solution required rejecting the assumption that drove every frontier heating decision. Everyone believed that faster heat was better heat, that immediate warmth from a hot iron surface was more practical than delayed warmth from stored thermal mass. Jonas suspected this assumption was wrong. A system that heated slowly but held heat longer would ultimately prove more efficient, more economical, and more comfortable than the quick heating, quick cooling method everyone accepted as superior. By spring of 1879, Jonas had decided to test the theory with his own materials and his own labor, regardless of what his neighbors thought about dirt pile stoves. Construction began in late April when the ground thawed enough to dig clay from a stream bed 200 yards from Jonas's cabin. The clay needed to be the right consistency, neither too sandy nor too dense. Jonas tested samples by rolling them into coils the thickness of his thumb. Good clay held together without cracking when bent into a circle. Too much sand and the mixture crumbled. Too much pure clay and it would shrink and crack when dried. The ideal mixture required 2 parts clay, 1 part sand, and chopped straw for binding. The most critical decision involved the path of the chimney. In a standard iron stove, hot exhaust gases traveled straight up and out, wasting most of their heat. Jonas designed a serpentine route that forced the gases to travel horizontally through channels inside the clay mass before finally exiting through the chimney top. This meant excavating precise pathways during construction, creating a maze that would capture heat without blocking airflow or creating dangerous backdrafts. Jonas began by positioning his existing cast iron stove in the center of the cabin's main room, then building around it rather than replacing it entirely. He constructed a base platform using flat stones from a nearby creek, raising the stove 6 inches off the cabin floor to prevent moisture from rotting the wooden floorboards underneath the heavy clay construction. The platform measured 8 feet long by 6 feet wide, large enough to support the massive structure he planned to build. The firebox required special attention because it would experience the highest temperatures. Jonas lined the interior of his iron stove with fire bricks purchased from the general store at 50 cents each. These bricks could withstand heat that would crack ordinary clay or damage the iron. Around the firebox, he built the first layer of clay mixture, packing it firmly but leaving precise openings for the flue channels. The internal channel system required careful engineering. Jonas created the first horizontal channel by laying flat stones as a floor, then building clay walls 8 inches apart on either side. The channel started at the back of the firebox, traveled toward the rear wall of the cabin, then turned 90 degrees and ran parallel to the back wall for 4 feet, before turning again toward the front of the cabin. This created a path roughly 16 feet long inside a mass that measured only 8 feet by 6 feet. The hot gases had to travel this entire distance, giving up their heat to the surrounding clay before reaching the final vertical chimney that exited through the cabin roof. Each layer of clay required specific timing. Jonas mixed batches using a wooden paddle in a wheelbarrow, adding water gradually until the mixture held together when squeezed but didn't stick excessively to his hands. He applied each layer 6 inches thick, smoothing the surface with wet hands and ensuring no air pockets remained trapped inside. Air pockets would expand when heated and crack the structure. The entire mass needed to be dense and uniform. The most challenging aspect was maintaining the channel openings while building upward. Jonas used temporary wooden forms cut from scrap lumber to hold the channel shape while he packed clay around them. After each section hardened for 2 days, he carefully removed the wooden forms, leaving hollow passages exactly where the hot gases needed to travel. If a form stuck or broke during removal, the entire section had to be rebuilt. Building the mass required 3 weeks of daily work. Jonas rose before dawn each day to mix clay and continue construction before the morning sun made the work uncomfortable. The finished structure stood 4 feet high, weighed approximately 2 tons, and resembled a large earthen mound with the iron stove door visible at one end and a single chimney pipe emerging from the top. Neighbors passing by commented that it looked like a giant anthill or burial mound rather than a heating system. The first test came in early May, during an unseasonably cold night when temperatures dropped to 35 degrees Fahrenheit. Jonas loaded the firebox with split oak, the best hardwood he could obtain, and lit the fire at sunset. He burned the wood steadily for 3 hours, maintaining a hot fire that heated the iron stove to its maximum safe temperature. At 10 o'clock, he allowed the fire to die completely, leaving only glowing coals that gradually burned out. Jonas measured the cabin temperature every 2 hours through the night using a mercury thermometer hung 3 feet from the clay mass. At midnight, 2 hours after the fire died, the cabin interior registered 71 degrees Fahrenheit. At 2 in the morning, the temperature held at 68 degrees. At 4 o'clock, it measured 65 degrees. At 6 in the morning, 8 hours after the fire had completely expired, the cabin remained at 62 degrees Fahrenheit. For comparison, Jonas repeated the test using only his iron stove without the clay mass. He burned the same amount of wood for the same duration, then measured temperatures through the night. 2 hours after the fire died, the cabin interior had dropped to 53 degrees Fahrenheit. By morning, it registered 41 degrees. The difference was dramatic and measurable. The fuel consumption comparison proved equally significant. During the clay mass test, Jonas burned approximately 1/8 cord of split oak. During the iron stove test, he required 1/4 cord of the same wood to achieve inferior results. The clay mass delivered longer-lasting warmth using exactly half the fuel of the standard method. More importantly, Jonas discovered that the clay mass radiated heat evenly throughout the cabin space rather than creating hot and cold zones. The iron stove heated the air immediately around it to uncomfortable levels while leaving the corners of the cabin cold. The clay mass warmed the entire room to a consistent, comfortable temperature that required no adjustment or management once the initial fire burned out. The success exceeded even Jonas's expectations based on his father's descriptions. The system worked precisely as the old world knowledge promised, but adapted to frontier materials and conditions. The clay mass had transformed his cabin from a space that required constant fire management into a space that stayed comfortably warm all night after a single evening burn. The first serious problems emerged in June during a humid spell when morning dew soaked the clay mass. Jonas lit his usual evening fire, but instead of drawing cleanly up the chimney, smoke began seeping through hairline cracks in the clay surface. The cabin filled with acrid smoke that burned his eyes and throat. Worse, the fire struggled to maintain proper draft, burning sluggishly and producing excessive creosote that could ignite and create a chimney fire. Jonas realized that moisture was the enemy of clay construction. When water penetrated the mass, it created steam during heating that forced its way out through the weakest points in the structure. The original clay mixture, perfectly adequate for dry conditions, became unstable when exposed to Nebraska's unpredictable humidity. He needed a solution that would seal the surface while allowing the internal structure to expand and contract safely during heating cycles. The answer came from Lars Andersen, a mason who had arrived from Denmark the previous spring. Lars had built tile stoves in Copenhagen and understood the relationship between moisture, clay, and high-temperature operation. He explained that European craftsmen applied a final plaster layer using lime mixed with fine sand and chopped horsehair. The lime hardened into a waterproof surface that prevented moisture infiltration, while the horsehair provided flexible reinforcement that resisted cracking during thermal expansion. Lime was available at the general store, imported from quarries in eastern Kansas at 15 cents per 50-pound bag. Jonas mixed the lime plaster using 3 parts lime, 2 parts fine sand sifted through window screen, and 1 handful of horsehair cut into inch-long segments per bucket of mixture. The horsehair came from his neighbor's workhorse, carefully cleaned and chopped with scissors. This final coating required application in thin layers, each one smoothed with a wooden float and allowed to cure for 3 days before applying the next. More critical was improving the combustion process itself. Lars explained that efficient burning required controlling the air supply to create complete combustion of wood gases. Most frontier stoves allowed too much air, which cooled the fire and created smoky, incomplete burning. Jonas needed to restrict the air intake and add a secondary air source higher in the firebox, where volatile gases could burn completely before entering the flue channels. Jonas modified his firebox by installing a damper in the primary air intake beneath the fire grate. This allowed him to control exactly how much air reached the burning wood. He also drilled holes in the iron stove side 6 inches above the fire grate and connected them to a separate air intake pipe that drew outside air directly into the upper combustion zone. This secondary air supply ensured that wood gases burned completely at high temperature rather than smoldering and creating creosote deposits in the flue channels. The draft control system required precise calibration. Too little primary air and the fire wouldn't start properly. Too much and the fire burned wastefully without heating the mass effectively. Jonas discovered that the damper needed to be fully open during the initial lighting phase, then gradually closed as the fire established itself. Once the clay mass began absorbing heat, he could close the primary damper to 3/4 position and rely on the secondary air to maintain clean combustion. Testing the improved system during a rainy week in July proved the modifications successful. Jonas lit fires each evening despite humid conditions and experienced no smoke infiltration into the cabin. The lime plaster surface remained intact with no visible cracks. More importantly, the controlled air supply created much hotter fires that heated the clay mass more efficiently while using less wood. The secondary combustion principle revealed itself clearly during these tests. With adequate secondary air, Jonas observed bright yellow flames dancing above the primary fire, indicating that wood gases were burning completely. Without secondary air, these same gases escaped unburned, wasting fuel and creating smoke. The temperature difference was measurable. Using a metal rod inserted into the upper firebox, Jonas recorded temperatures of 1200 degrees Fahrenheit with secondary air engaged compared to 800 degrees without it. Draft problems persisted during certain weather conditions, particularly when atmospheric pressure was low or wind direction created downdrafts. Jonas solved this by extending his chimney pipe 2 feet higher above the cabin roof and installing a simple wind cap that prevented downdrafts while maintaining proper exhaust flow. The wind cap consisted of a larger pipe section placed over the chimney top with 4 vertical slots cut to allow smoke to exit while deflecting wind. Creosote management became routine rather than crisis. Jonas installed a clean-out door at the bottom of the main flue channel, accessible by removing a single clay brick he had left loose for this purpose. Every 2 weeks, he scraped accumulated creosote from the flue using a long-handled scraper made from a hoe blade. The secondary combustion system reduced creosote formation significantly, but regular cleaning remained essential for safe operation. The most dangerous oversight in Jonas's original design was carbon monoxide detection. Lars warned that incomplete combustion or blocked flues could allow deadly gases to leak into the cabin. Jonas learned to recognize the signs of improper combustion, weak draft, smoke smell inside the cabin, or unusually drowsy feelings during evening fires. He installed a simple test by hanging a piece of white cloth near the stove. If the cloth showed yellow staining, combustion gases were escaping, and the system needed immediate attention. By August, Jonas had refined the system to operate safely in all weather conditions. The lime-sealed surface shed rainwater completely. The controlled air supply produced clean, hot fires that heated the mass efficiently. The extended chimney with wind cap maintained proper draft regardless of wind direction. The clean-out system made maintenance simple and regular. The performance improvements were substantial. Where the original design had delivered 8 hours of warmth from a 3-hour burn, the refined system provided 12 hours of consistent heat from the same fuel load. The cabin temperature remained more stable throughout the heating cycle, varying by only 3 degrees Fahrenheit rather than the 8-degree swings of the earlier version. Most significantly, Jonas had eliminated the safety risks that could have discredited the entire approach. No smoke infiltration, no creosote fires, no carbon monoxide exposure, no structural failures due to moisture damage. The system now operated as safely as any conventional stove while delivering far superior performance. The foundation was established for proving the concept during the severe test of a full prairie. Winter. Winter arrived early in 1879 with a blizzard in late October that lasted 4 days and consumed most settlers' carefully hoarded wood supplies. Jonas faced the same crisis as his neighbors, but with a crucial advantage. His clay mass system had been designed and tested using quality hardwood, but the real frontier test required burning whatever fuel could be gathered from the prairie itself. The fuel crisis forced innovation in gathering techniques. Jonas discovered that buffalo chips, the dried manure scattered across the plains by migrating herds, burned differently than wood but could be adapted to his system. The chips burned very hot but very fast, creating intense heat for 20 to 30 minutes before reducing to ash. This seemed incompatible with heating a massive clay structure that required sustained heat input to reach full temperature. Jonas solved the problem by developing a loading technique that maintained continuous high heat despite the short burn time of individual fuel pieces. Instead of loading the firebox once and letting it burn down, he fed small amounts of chips every 10 minutes for the first hour of heating. This maintained the interior temperature above 1,000 degrees Fahrenheit, long enough to heat the clay mass thoroughly. Once the mass reached operating temperature, the remaining chips could burn out completely while the stored heat continued radiating for hours. Prairie grass bundles required different handling entirely. Jonas learned to twist dried grass into tight bundles using techniques borrowed from haymaking, creating dense fuel packages that burned longer than loose grass but still much faster than wood. The key innovation was mixing grass bundles with buffalo chips in specific ratios. 2 parts chips to 1 part grass bundles provided steady heat output for 90 minutes, sufficient to charge the clay mass fully. Sunflower stalks, abundant after harvest, presented unique challenges and opportunities. The hollow stems burned explosively when dried, creating dangerous flare-ups that could crack the fire bricks if not controlled properly. Jonas learned to split the stalks lengthwise and remove the pithy interior, leaving dense outer shell material that burned more predictably. Bundled split stalks mixed with chips created fuel loads that approximated the heating characteristics of softwood, though requiring more careful attention during the lighting phase. The most significant adaptation involved modifying his air control system for different fuel types. Prairie fuels required more primary air than wood because they contained less dense carbon and more volatile materials. Jonas adjusted his damper settings, opening the primary air intake wider when burning chips or grass and relying less on secondary air. This prevented the smoldering combustion that wasted prairie fuels and created excessive smoke. Fuel storage became a critical frontier skill. Unlike wood, which could be stacked outdoors indefinitely, prairie fuels degraded rapidly when exposed to moisture. Jonas constructed a simple storage system using his cabin's small loft space. He spread buffalo chips in single layers on boards, allowing air circulation to keep them completely dry. Grass bundles hung from rafters in mesh bags made from old grain sacks. Sunflower stalks stood in bundles against the loft walls. This indoor storage ensured dry fuel, regardless of weather conditions. The economics of prairie fuel proved dramatically superior to purchasing wood. Jonas calculated that gathering buffalo chips required approximately 4 hours of work to collect fuel equivalent to one purchased cord of wood. At prevailing prices, this represented a labor value of 50 cents per hour, higher than most frontier work paid. More importantly, buffalo chips were renewable. Migrating herds deposited fresh supplies each spring and fall, creating a sustainable fuel source that required no transportation costs. Ash management became more complex with prairie fuels. Buffalo chips produced fine powdery ash in quantities much larger than wood ash. Jonas modified his firebox by installing a larger ash drawer and developing a weekly ash removal routine. The ash itself proved valuable as fertilizer for the small garden plot behind his cabin, containing concentrated nutrients from prairie grasses consumed by the buffalo. The testing phase required careful measurement during actual cold weather. In November, Jonas conducted a direct comparison using identical weather conditions. On successive nights, when outside temperatures reached 15 degrees Fahrenheit, he heated his cabin first using purchased wood, then using gathered prairie fuel. The wood test used 1/8 cord of split oak and maintained interior temperature at 68 degrees for 10 hours. The prairie fuel test used 2-bushel baskets of buffalo chips mixed with grass bundles, costing nothing but 4 hours of gathering time, and maintained interior temperature at 65 degrees for 9 hours. The slight reduction in performance was more than offset by the economic advantage. Jonas calculated his total winter heating cost using prairie fuels at $0 cash expense versus an estimated $18 for purchased wood. For a homesteader operating on limited cash income, this difference determined whether money remained available for other essential supplies like flour, coffee, and lamp oil. Durability testing revealed unexpected benefits of the prairie fuel system. The lower sulfur content of buffalo chips compared to coal reduced corrosion of his iron stove components. The fine ash created minimal creosote buildup in the flue channels, reducing cleaning frequency from weekly to monthly. Most importantly, the clay mass showed no degradation despite burning different fuel types throughout the heating season. Jonas also discovered that prairie fuels provided superior overnight heating, characteristics for his specific system. Wood fires tended to create temperature spikes that could overheat the clay mass, leading to uncomfortable indoor temperatures and wasted heat. Prairie fuels burned at more moderate peak temperatures, but maintained heat output more consistently during the critical mass charging period. This matched the thermal characteristics of his clay system more effectively than wood fires. By December, Jonas had refined his prairie fuel techniques to the point where his cabin stayed more consistently comfortable than wood-heated cabins, despite using only materials gathered freely from the surrounding landscape. His neighbors began asking detailed questions about fuel gathering locations, storage methods, and burning techniques. The economic advantages were too significant to ignore, particularly during a winter when wood prices rose to $3 per cord due to supply shortages. The success with prairie fuels proved that his clay mass system was not dependent on expensive or scarce materials for either construction or operation. Local clay, river sand, and wheat straw for the structure, buffalo chips, prairie grass, and crop residues for fuel. The entire system could be built and operated using only materials available within walking distance of any prairie homestead, making it accessible to settlers regardless of their cash resources or proximity to timber supplies. The ultimate test arrived in January 1880, with a weather pattern that meteorologists would later call the Great Cold. Arctic air settled over the Central Plains and remained stationary for 18 consecutive days, with daytime temperatures never rising above 0 degrees Fahrenheit and nighttime readings dropping to 25 degrees below zero. Worse than the cold was the timing. The deep freeze struck immediately after a 3-day blizzard that made travel impossible and cut off supply lines to prairie settlements. Jonas faced the crisis with a critical tactical advantage that became apparent only under extreme conditions. His clay mass system required front-loading the fuel investment rather than maintaining continuous burns throughout long cold periods. He could charge the thermal mass to maximum capacity once per day and rely on stored heat rather than competing with neighbors for increasingly scarce fuel supplies during the emergency. The strategy required precise heat management techniques Jonas had not needed during normal winter conditions. He developed a maximum loading protocol that pushed his system to its thermal limits safely. Starting with a cold firebox, he built the fire gradually using small amounts of buffalo chips, allowing the clay mass to heat slowly for the first hour to prevent thermal shock cracking. Once the mass reached 600 degrees Fahrenheit internally, measured using a metal rod inserted through a test hole, he could increase the fire intensity dramatically. The peak loading phase involved him burning fuel continuously for 4 hours instead of his normal 2-hour charging period. Jonas fed buffalo chips steadily, maintaining firebox temperatures above 1200 degrees Fahrenheit for the extended duration. This drove the clay mass to maximum heat storage capacity, creating an internal temperature approaching 800 degrees Fahrenheit throughout the entire 2-ton structure. The technique required constant attention and consumed roughly 3 times his normal daily fuel load, but the payoff was proportional. Under maximum loading, the clay mass delivered radiant heat for 36 hours instead of the normal 12-hour cycle. Jonas measured interior cabin temperatures starting immediately after the 4-hour burn ended completely. At 12 hours post-burn, the cabin remained at 72 degrees Fahrenheit. At 24 hours, it measured 68 degrees. At 36 hours, the temperature still registered 62 degrees, comfortable for sleeping even with outside air at 25 degrees below zero. This extended heating cycle proved crucial during the supply crisis because it allowed Jonas to skip heating on alternate days, reducing his fuel consumption to half the normal rate precisely when fuel was scarcest. While neighbors burned every available combustible material daily just to prevent freezing, Jonas heated his cabin every other day and maintained superior comfort levels throughout the crisis period. The social dynamics shifted dramatically as the crisis deepened. Carl Bergman, who had mocked the dirt pile concept 2 years earlier, appeared at Jonas's door on day 12 of the freeze. Carl's cabin had dropped to 38 degrees Fahrenheit, despite burning furniture, fence posts, and the wooden handles from his farming tools. His children showed early signs of frostbite, and his wife had developed a persistent cough from sleeping in near-freezing conditions. Carl asked directly whether Jonas would share his heating technique. Jonas agreed to provide technical assistance but insisted on complete construction details rather than shortcuts. Carl needed to understand that the system required substantial upfront labor and material investment, not quick modifications to existing iron stoves. Jonas walked Carl through clay testing, channel layout, air control principles, and fuel loading techniques. More importantly, he explained that the system's advantages appeared only during sustained operation, not immediately after construction. Word spread through the settlement as other families faced similar heating failures. Martha Lindgren visited on day 15, accompanied by the Anderson family and 2 other neighbors. Jonas found himself conducting impromptu technical seminars in his warm cabin while his visitors shivered despite wearing all their available clothing. The contrast was impossible to ignore. Jonas sat comfortably in shirt sleeves while his guests huddled around his clay mass, wearing coats and blankets. The most convincing demonstration involved fuel consumption measurements. Jonas invited his neighbors to examine his fuel storage area and estimate his remaining supplies. Despite 18 days of severe cold, Jonas retained sufficient buffalo chips and prairie grass bundles to continue heating for another month at normal consumption rates. His neighbors had exhausted their fuel supplies and were burning household items, clothing, books, and anything else that would combust. The economic implications became undeniable when supply wagons finally reached the settlement after the weather broke. Wood prices had increased to $5 per cord, more than triple normal rates. Families who had burned emergency supplies faced bills exceeding $25 for winter heating, equivalent to 2 months of farm income. Jonas had spent nothing beyond his autumn labor gathering prairie fuels that remained abundant and freely available. 3 families committed to building clay mass systems before the following winter. Lars Anderson agreed to provide masonry consultation for all 3 projects in exchange for help with his own farm work during spring planting. Jonas offered to supervise construction and share his refined techniques for clay mixing, channel design, and air control systems. The knowledge that had seemed eccentric and impractical 18 months earlier was now viewed as essential survival technology. The replication process revealed the system's scalability and adaptability. The Anderson family built a smaller version suitable for their single-room cabin, using 3/4 the clay mass and shortened flue channels. The Lindgrens constructed a larger system designed to heat two rooms simultaneously, requiring dual flue paths and more complex air management. Each adaptation required technical modifications, but the basic thermal mass principle worked effectively in all configurations. By the following autumn, 7 families in the settlement had constructed clay mass heating systems based on Jonas's design. The local general store began stocking fire brick and lime in larger quantities, responding to demand from the growing community of clay stove builders. Lars Anderson's masonry skills became essential to the settlement, establishing him as the technical expert for advanced construction details. The validation extended beyond immediate survival benefits. Families using clay mass systems reported improved health during winter months, with fewer respiratory complaints and cold-related illnesses. Children slept better in consistently warm cabins rather than enduring the temperature swings of iron stove heating. Women appreciated the reduction in daily fire management tasks, freeing time for other household work during short winter days. Jonas's innovation had transformed from personal experiment to community standard, proving that traditional thermal mass principles could be successfully adapted to frontier conditions using local materials and practical construction techniques. The mocked dirt pile had become the foundation of a heating revolution that would influence prairie homestead design for decades, demonstrating that survival often required combining old world knowledge with new world resourcefulness under conditions that demanded both technical precision and practical adaptability.